Namaskar and welcome to this second lecture in this course on hydration, porosity and strength of cementitious materials. And here in this lecture we will concentrate on talking about a model of concrete as a three-phase system. The list of textbooks and reference materials is included for you to be able to get additional knowledge, information and so on relating to some of the subjects that we'll talk about. This lecture will help us in better understand a model of concrete based on its basic constituents and how issues such as strength, load transfer and durability can be looked upon in the suggested framework. Concrete is presented as a three-phase system: the aggregate, mortar, which is also the binder, and the interface. The importance of the interfacial transition zone of concrete, with an emphasis on the role that it plays in the strength and material transport, is what we will seek to discuss today. We will talk about understanding the phases in concrete, behavior of these phases under load, and the ITZ or the interfacial transition zone. So let's take a look at this picture which we saw in the first lecture as well, which is basically a photograph of what concrete looks like on the inside. We can schematically represent this as coarse aggregates and mortar in a manner that the coarse aggregates here, which is these coarse aggregate particles, are suspended in mortar or cement paste and fine aggregate. We must remember that even in the fresh state, this must be the configuration, or this must have been the configuration, even though we have taken the picture in the hardened state. Now, if we were to understand this model if we were to look at this model more closely, we can model it as a series representation where we will say that from a load application point of view, if the load is being applied like this, all this mortar here is lumped at one place, shown here, and all this coarse aggregate here is lumped at one place, that is shown here. And these two phases are in series as far as the load application is concerned. Another representation could be when the phases are in parallel. Now what that means is that we have a situation like this, where the same amount of mortar and the same mortar is placed here, and the coarse aggregates are placed here, and the load is applied this way. Now if we look at the action of this concrete, which is the real concrete, under the action of load, when the phases are in series, what we will have is a system like this. Now, basic physics tells us that in this case, both the mortar and the coarse aggregate will carry the same load. Having said that, the stresses in the mortar and the coarse aggregate will be the same. Now, if the stresses are the same and the modulus of elasticity of these two phases is different, the strains in the mortar and coarse aggregates will be different. So this is how the situation will pan out if the mortar phase and the coarse aggregate phase was taken to be in series. If we take the situation now when the two phases are in parallel, then the load carrying mechanism suggests that both the mortar and the coarse aggregate will be subjected to the same level of strain. That is, they have to deform to the same level. And now, if the level of deformation, which is the strain, is the same, then the load that they carry, which is related to the stress, will be different. But concrete in the real sense, which is this picture, is neither a truly parallel system nor is it a truly series system. We have an actual behavior which is somewhere in between the series and parallel mechanisms of load transfer. So this we must remember at the back of our mind when we are trying to understand the action of concrete under load. Now let's talk about the interface. At the end of it, the mortar and the coarse aggregate are not necessarily monolithic. The coarse aggregate particles are only suspended in mortar. And if we look at the role of this interface when the phases are in series, if we say that, well, there is an interface in between, what is the importance of that interface? So long as we are talking of a series model, the role of that interface is not very critical, because the load being carried by this and this phase is all the same, and it's only the deformations which are different. Whereas if it comes to a model where the phases are in parallel and we have an interface between the coarse aggregate and the mortar phase, there this role is very important, because we must ensure that there is proper bond between the coarse aggregate phase and the mortar phase in order to ensure strain compatibility. We can therefore more or less come to a conclusion that concrete is a three-phase material, with the three phases being coarse aggregate, mortar, and the interface itself. Now this interface is a formal entity which we have introduced between the mortar and the coarse aggregate. And this entity exists in this form if we are talking of the so-called series system, where if the load is applied like this, the interface is the way it is shown here, and the interface is in this configuration for a system where the phases are in parallel. Now let us look at the interfacial transition zone once again. This is our model concrete where coarse aggregate particles are suspended in mortar. We have this ITZ, which is a small zone between the mortar phase and the coarse aggregate phase. In other words, what we have said is that the zone of paste surrounding the aggregate particle in concrete is termed as the interfacial transition zone and is popularly known as the ITZ. In other words, what it means is that each of these aggregate particles which are shown here is actually surrounded by this ITZ. Now this ITZ actually comes about as a result of bleeding, as a result of small amounts of segregation that occur in the neighborhood of an aggregate particle as some particles try to settle down under the action of gravity, resulting in accumulation of water around these aggregate particles. As a result of that, effectively, the water cement ratio in the ITZ is slightly higher than that of the main body of the mortar. Effectively, once again, the interface is closer to the mortar phase in properties. See, there is no way that we can argue that this interface between the aggregate particles and the mortar is close to the aggregate, because the aggregate has a very well defined geometry, whereas the mortar is filling the space. And like I said before, because of small amounts of segregation that happen around the aggregate, we have the formation of this interfacial transition zone, the ITZ. Now this ITZ is close to the mortar phase in its properties, but is weaker than the main body of the mortar because of the formation of bleed channels arising out of bleeding, and the effective water cement ratio in that small area, or that is small volume around the coarse aggregates, being slightly higher. As far as the mortar phase is concerned, we can talk of the properties of the main body of the mortar, which is here, and the mortar which is existing in the ITZ, with the mortar in the ITZ being slightly weaker than the main body mortar. What are the implications of having this weaker ITZ in the neighborhood of the coarse aggregates? One implication is that the ITZ is more prone to microcracking because of its weaker strength. To summarize, the importance of this ITZ can be understood in the following aspects. One is strength and cracking, and the second is from the point of view of durability and material transport. If we read literature about what governs the strength of the concrete, the traditional wisdom is the water cement ratio. And indeed, water cement ratio governs the strength of this mortar, because that is exactly where we are trying to control the extent of porosity and so on, and we can control the strength of this overall matrix through the control on the strength of mortar. But just now we argued that the strength of this ITZ is slightly lower than that of the main body mortar, and therefore the ITZ becomes the strength limiting phase in concrete, and cracks propagate rapidly through this interface. As far as the durability issues are concerned, ITZ eases the penetration of external agents. Basically, if the strength of the ITZ is lower, it is also an indication of the fact that the porosity in the ITZ is higher. Now, if the porosity of the ITZ is higher, the material transport, that is the penetration of external agents, whether it is carbon dioxide or it is chloride ions or it is sulfate ions, all this would be easier through the ITZ than through the main body of the mortar. It's the presence of the micro cracks and the fact that there are more pores in the ITZ, that is what makes the ITZ more vulnerable for penetration. It's more permeable. So with this, what we did today was try to understand the phases of concrete, that is the coarse aggregate, mortar, and the ITZ. We tried to look at the action of concrete under the load if the two phases were taken in series or the two phases were taken in parallel, and argued that so long as the phases were in series, the ITZ has limited role to play as far as strength is concerned, but it will of course have the same amount of impact as far as durability and material transport is concerned. But if the phases are in parallel, then the ITZ plays an important part in even determining the strength and ensuring strain compatibility between the coarse aggregate phase and the mortar phase. And we talked a little bit about the importance of the ITZ from the point of view of strength and durability. And with this, I'd like to thank you for your attention and look forward to seeing you again.